good morning students. Okay, so in this video we'll have look at another example. Okay, we'll take a much complex boolean expression and let us try to draw the stick diagram for it. Okay, so let the boolean expression be one second, let me maximize this one. Okay, so this should be clear. So let the boolean expression be f is equal to ab plus c into d plus e whole complement. Okay, right. So let us draw the CMOS implementation for this first. Okay, let me draw the pull down network first. Okay, so AB, it is an AND gate, so those two will be in series. Now this AB term is being ORed with C into D plus E. Again, if there is an AND here, that is nothing but series. So this C is in series with what? D plus E. D plus E is nothing but OR. Okay, so OR of D plus E. So this is nothing but ground. So this is this transistor is A, this is B, this transistor is my C, this transistor is my D, and this transistor is my E. Okay, now let me draw the pull-up network. Okay, so pull-up network is between VDD and F. Pull down is in between F and ground. Okay, now what is the first term? AB and operation in pull-up network. Okay, so they'll be in parallel. Okay, so B and in parallel, and AB is being ORed with something else. OR operation in pull-up network means series. Okay, so this is in series with C into D plus E. Okay, so this is in series with C here, but this C is being ANDed, and in pull-up network means parallel. Okay, so this is being ANDed with OR of D and D. Okay, OR of D and D is nothing but series in PMOS. Okay, so that is something like this, C D E. Okay, so that should finish our CMOS representation of the given Boolean function. Okay, now the second step is we need to come up with the graphs. Okay, let me draw the pull down graph first. Okay, so the pull down graph is between we know between F and ground. Okay, so each transistor is an edge. Okay, so between F and ground we have A and B. Okay, between F and ground we have A and B. Between F and ground we also have C and D and E in parallel. Okay, so this is C and this is my D and this is my E. Okay, so this is the graph of my pull down network. Okay, similarly, what is the graph of my pull up network? My pull up network is always present between VDD and F. Okay, what do I have? Of course this is A, so A and B, these two transistors are in parallel. Okay, and that common node is going to F from C via C. Okay, and from this point to F also we have two more transistors, so we'll have two more edges over here. So this is nothing but D and E. Now we need to find a path. Okay, so let me label this. This is graph of pull-up network. We need to find a path. Basic thing is we need to cover all the nodes, but what is the constraint? We can traverse through an edge only once. We need to cover all the vertices, but we can traverse through the edges only once. Okay, so let me see how I will be traversing through all the nodes here. I should be covering all the nodes. Okay, so if I take the path A, B, D, E, I cannot go back because this path I have taken already. Okay, now let me take this example wherein I'll take E, D, C, A, B. I covered all the nodes, right? And traverse through all the edges only once. See, E, D, C, A, B. Okay, so EDCAB is a path. Remember, we are computing the Euler's path, and that path has to be common in both pull up and pull down. Now let us see if EDCAB, okay, is applicable for pull up. Okay, so this is E, D, C, and if I have to traverse AB, I have to go back through C, but this edge I already covered. Okay, so EDCAB is not a Euler's path. Okay, let us see DECAB. Okay, so DECAB is a path, so that is covering all the nodes and while traversing the edges only once, right? So this is DECAB. Okay, so DECAB is a path. Let us see here. So DECAB is a path here too. Okay, so DECAB is satisfying this one too. So DECAB is my Euler's path. So what is the Euler's path that we identified? So the Euler's path is nothing but D, E, C, A and B. Okay, now let us draw the stick diagram. So let me copy this. Okay. Okay, let me have this here for quick reference. Okay, right. So DECAB is the Euler's path. Okay, now let me draw the stick diagram for it. Okay, so DECAB is my Euler's path. So what is the first step in drawing any stick diagram? We draw VDD and ground. Okay, let me deselect this. Okay, so we draw okay, so this is my VDD and this is my ground. VDD and ground are always in blue because they are connected in metal. Okay, and we know that NMOS transistors are near to the ground, and we know that N diffusion is green in color. So this is my N diffusion, and we know that PMOS transistors are made of P diffusion, and P diffusion is yellow in color. So I take the yellow color and I draw it near VDD. Okay, now what is the Euler's path? I draw the poly. Now poly is red. Total I have to make 10 transistors. Okay, 5 in PMOS, 5 in NMOS. Okay, so I follow the Euler's path. This is nothing but D, this is E, this is C, this is A, and this is B. Okay, so let me label this D, C, A and B. Okay, so this is also D, E, C, A and B. Okay, so I have the D transistor, E, C, A and B. These are NMOS, and D, E, C, A, B. So these are my PMOS transistors that are ready. Now I have to make the interconnections. Okay, now let us look at the graphs and make the interconnections. Okay, so what is happening here? The common point okay, of D and E is ground. Okay, so this is nothing but my common point of D and E, isn't it? Okay, so where is that connected to? That is connected to ground. Okay, so the other end of D, okay, is connected to common point of E and C. Okay, see, the other end of D is nothing but this one. Okay, this is connected to common point of E and C. Okay, so this is my common point of E and C, and where is that connected? That is connected to other end of D. So other end of D. Now this junction is done. Okay, so these connections are also done. Okay, so the other one end of C has already been connected to E and D, so this connection is done. So what is the other end of C doing? The other end of C is connected to one end of A and F. Okay, see here, other end of C is directly connected to A. Okay, because those two are connected via the diffusion, but those two are also, if you see, are connected to F. Okay, so I need to make a connection to F. Okay, so I take this common point here, and this I make a connection to F. So this connection, this node is also made. So one end of A is connected to F, the other end of A is connected to B. See here, one end of A is connected to F, the other end of A is connected to B via this end diffusion, so I don't not need to make any explicit connections over here. So this connection is already made, this connection is already made. Okay, what is happening to the other end of B? The other end of B is connected to ground. Okay, I have to make this connection. So other end of B, I have to connect that to ground. Of course, I need to use metal. Metal is nothing but blue. Okay, so that finishes my NMOS. Okay, so that finishes my NMOS. Okay, so let me start with my PMOS network now. See here, one common point of AB is connected to VDD. Okay, so that is common point of AB is this thing. Okay, so this is sorry, this is connected to VDD. Okay, so common point is connected to VDD, and the other end of AB is connected to C and D as well. Okay, so C, so A and C are connected at this point. At the same point, one end of B and one end of D are also connected. Okay, so A and C are connected at this point. What is also connected at this point? One end of B, that is this one, and what is also connected at this point? One end of D. Okay, so I can make it at this point. Okay, so now let us finish the connections. Okay, so at this point A and C are already connected. At this point, see, I have A, B, C and D coming, 4 connections here. So 2 connections are already made. I need 2 more connections. So this also needs to be connected to one end of B. Okay, this also needs to be connected to one end of B. Okay, the same point also should be connected to one end of D. The same point should also be connected to one end of D. Remember, I forgot to mention, your metals should not cross in your stick diagrams. So 2 metal connections cannot cross each other. That is, I cannot draw a connections like this. No, metal connections should always be separate. Okay, see here, this connection is not overlapping this with this connection and so on. Okay, but if you identify your Euler's path correctly and draw the stick diagram, you won't have any overlapping metal connections. That is the beauty of finding the Euler's path. Okay, so Euler's path has that advantage. It directly gives you a solution so that no metals are overlapping. Okay, that is the beauty. Okay, now this connection is also done. Okay, so this end of C is done. What is the other end of C connected to? The other end of C is connected to E. Okay, so the other end of C is connected to E, and both are connected to F. Okay, so other end of C is connected to E, and these two are connected to F. Okay, right. Okay, so that connection is done. So this connections is also done, and one end of E is connected to F. Yes, very good, this connection is done. The other end of E is connected to D, that is this point. The other end of E is connected to D. So this connection is already made here because this is a common diffusion. This connection is already made. Okay, so that finishes my pull-up network as well. So this is my stick diagram for F is equal to, okay, AB plus C into D plus E whole complement. Okay, so this is the stick diagram. Okay, you need more practice. Okay, so I'll give you a good number of assignments. Okay, I'll give you some 10 to 12 problems. Okay, so if you do 10 to 12 problems, okay, you will become masters at the stick diagrams. Okay, right, if you have any doubts, please do ping me or mail me or telegram me. Okay, thank you.